Last week in week 3, we saw how to use the simplex algorithm to find the optimal solution to linear programming problems where the constraints were all of this form. They were all of the form linear expression less than or equal to non-negative resource value B. Today we're going to look and see how we can treat the case where some of the inequalities might be greater than or equal to non-negative resource value B. And this is slightly different. There are two methods. They're very, very closely related, but distinct methods. One's called the two-phase method and the other is called the big M method. I'm going to explain these methods by way of examples, and I'm going to look at this very simple example here where we've got a maximization problem with two decision variables and two constraints. And you notice here the first constraint is the same kind of constraint we considered last week, but the second constraint isn't. It's here greater than or equal to a non-negative number. And the important thing here is that the origin 0, 0 is not a corner of the feasible region because 0, 0 doesn't satisfy this second inequality. So our method from last week won't work. You recall the simplex algorithm idea is to start at a corner of the feasible region and move from corner to corner till you find the optimal value. Now the two-phase method begins somewhat similar to the method we had last week by introducing slack variables S1 and S2 corresponding to the two inequalities, but now the second slack variable will have a negative coefficient. And the reason is that the slack variable takes up the slack between the two sides. And in the second inequality, the left-hand side is greater than or equal to the right-hand side. So if we want to keep our variables to be non-negative, we need to subtract a variable from the left-hand side, which is why we have minus S2 here. So these inequalities, we might regard them as the bad inequalities. These are the ones we didn't treat last week. And whenever we have a bad inequality, the slack variable will be negative, have a negative coefficient. The next step is to introduce a thing called the artificial variable. The artificial variable is something we didn't have at all last week, and it'll have a particular use, which we'll see in a minute. It's called an artificial variable because we're really interested in these equations. We introduce the artificial variable, but we're going to look for the situation where this artificial variable is in fact 0. One of the reasons for, well, the reason for introducing it is that we can introduce it with positive coefficient, and then it can be our first basic variable. Now, before we write down the tableau, we need to look at what's going to be our objective function. Now, as I was just explaining, we're really interested in the case where this artificial variable is 0. So, in order to make it 0, because R1 is a non-negative number, we want to minimize R1. And to minimize R1 means to maximize minus R1. So the clever idea here in the two-phase method is to use linear programming to obtain the solution R1 equals 0. And this will correspond then to a corner of the feasible region. And then, once we get to that point, we can just continue as we did last week. Now, R1, you see back here, R1 is given by this equation. And so W, which is our new objective function, is minus R1, is given by this expression here. It comes from that equation. So, we start our tableau. Here is our first tableau up the top. Here are our original decision variables x1, x2. we have slack variables S1, S2, and we have our new artificial variable R1. These two rows correspond to the two inequalities. We've got the slack variable S1 with positive coefficient, the slack variable S2 with negative coefficient, but the artificial variable has coefficient 1. Here are the resource values 2 and 3. Our basic variables that we start with are S1 and R1. Here they are written over here. This is our objective function row for W. And I've also written here above it the objective function row for Z, because we'll need that later on. So the idea, first of all, is to just apply the linear programming problem and look for the variables for which W is maximized. Remember, we're trying to make R1 go to 0. So we just, we just go through this process, and when we've finished and we can't go on any further, we should have a 0 here, because we know that W has a maximum value of 0. So that's the first phase, and this will give us values for our variables x1 and x2. Here they are here. Values for our variables corresponding to a corner of the feasible region. And then having obtained those values, we can go on. And the way we go on is we simply eliminate the W row and the R1 column and continue. So we eliminate W row, R1 column. This gives us this new smaller tableau. And now our objective function is Z, which we've kept on with us all along, so it would still be there. And now we just apply our process as we did last week, and we continue the simplex algorithm to find the solution for Z, which in this problem turns out to be minus 15. So I encourage you to go back, make sure you can see how this process works, and then see how we get this tableau from the previous page, and then how the simplex algorithm gives us this final solution. And that's the two-phase method. See, it is in two phases. In phase 1, we are maximizing W. Once we get the value 0, we can't go on, there's no more negative numbers here. Then we move to phase 2, and for phase 2, we're looking to maximize Z. The Big M method is very, very similar, but there's just a single phase now. What we do in fact is we put the two phases together. So we start in the same way with our slack variables and our artificial variables, that's exactly the same. And we then introduce a new objective function, which is the old objective function minus m times R1, where m is some arbitrary, unknown, but very large positive number. The idea is it's much larger than any of the other numbers present. And the idea here is because we're maximizing Z dash, and because this m is so big, then this will, the effect of this will be to force R1 to go to 0, which will be exactly like the first phase of the two-phase method. Now, as before, we're going to replace R1 by the expression that it has given by this second equation. So we replace R1 by what we get from this one, and that gives us this expression here. And now we've got our single objective function. It's expressed in terms of the decision variables x1, x2, and the slack variables s1 and s2. We can write down the tableau. Here it is. You'll notice here that the m's are appearing in the objective function row. They don't appear anywhere in the body of the table. And then we just perform the simplex algorithm. We have to remember m has to be understood to be a very large positive number. So 7 minus m and 5 minus m are both negative. Well, 5 minus m is smaller than 7 minus m, so this is the biggest negative number. So that's definitely our column to work in. There's only one positive number here, so that must be the place where we pivot. And we pivot on that one, and it produces this tableau here. And we get the same answer as before. So you'll do examples of this in the practice class, and you'll need to become proficient in both methods.